Welcome to homework.
In this problem on the topic of atoms, we are told that the medium in a particular laser that is generating laser light of a wavelength of 694 nanometers is 6 centimeters in length and 1 centimeter in diameter. If the medium is behaving as an optical resonance cavity, similar to a closed organ pipe, we want to know how many standing wave nodes exist along the laser's axis. Now, we also want to know the amount delta F that the beam frequency will have to shift in order to increase this number by 1. We then want to show that delta F is just the inverse of the travel time of laser light for one round trip back and forth along the axis of the laser. Lastly, we want to find the corresponding fractional frequency shift delta F over F. Now, if both mirrors are partially reflecting, there's a node at each end of the crystal. With one end partially silvered, there is a node very close to that end. We assume nodes at both ends, so they are an integer number of wavelengths in the length of the crystal. And the wavelength in the crystal we'll call lambda c, and this is equal to lambda of the laser over n, where n is the index of refraction of ruby. And so therefore n times lambda over 2 times little n is equal to L, where big N is the number of standing wave nodes. So this means the number of standing wave nodes N is equal to 2 times the refractive index of ruby times the length of the cavity over lambda. And this is equal to 2 times the refractive index of 1.75 times the length 0.06 meters divided by the wavelength of the laser 694 times 10 to the minus 9 meters. And so we get this number to be 3.03 times 10 to the power 5. That's the number of standing wave nodes in the cavity. Now for part B, we know lambda is c over f, where f is the frequency. And so n is equal to 2 times little n times L f over c. And delta n is equal to 2n L over c times delta f, which means that the frequency change delta f needs to be c times delta n over 2 times little n times L. So this is the speed of light to 0.998 times 10 to the 8 meters per second, and delta n is shifting by 1, so this is just 1, divided by 2 times the refractive index of 1.75 times the length of the cavity 0.06 meters. And this gives us the frequency shift to be 1.43 times 10 to the 9 hertz. So that frequency change will provide one extra node. Now for part C, we want to show that delta F is simply the inverse of the travel time of the laser light for one round trip along the laser's axis. Now the speed of light in the crystal is c over n, and the round trip distance is 2L. So the round trip travel time t is equal to 2nl over c, which is the same as the reciprocal of the change in frequency. Next, for part D, we want to find the corresponding fractional frequency shift delta F over F. Now the fractional change in frequency delta f over f is equal to 1.43 times 10 to the 9 hertz divided by the frequency 4.32 times 10 to the 14 hertz, which gives us a fractional change of 3.31 times 10 to the minus 6.